A distant star is being watched, and then something impossible seems to happen. Its light drops sharply. Not by a small amount, not by the kind of change that would normally pass unnoticed. A huge portion of its brightness simply disappears. When Kepler records the behavior of Tabby's star, the dimming is irregular. There is no steady rhythm, no predictable pattern. The star brightens, then suddenly loses so much light that it looks as if a massive section has been removed from view. The numbers make a problem impossible to ignore. During some of these events, roughly 20% of the star's light vanishes. That immediately creates a failure. The explanation astronomers trust most for changing starlight depends on objects crossing in front of a star and blocking part of its glow. But drops this large do not fit what they normally expect to see. The observation remains, the light is missing. The usual explanation no longer feels secure. Whatever is happening around Tabby's star, it does not look like an ordinary dimming event. Something is removing an extraordinary amount of brightness, and the reason is still unknown. The simplest explanation is still alive, at least for a moment. If something is passing in front of the star, then another dimming event should eventually arrive. The pattern might be unusual, but a repeating orbit should leave traces of its schedule behind. So the observations continue. Another drop appears. Then another. But the behavior refuses to settle into a rhythm. The timing changes. A dimming event arrives when it is not expected. Then a longer gap follows. The depth changes. Then even the duration changes. Every new event behaves differently from the one before it, instead of repeating with the consistency expected from an object circling the star. That creates a practical problem. A normal orbiting object does more than explain what already happened. It allows future events to be predicted. Once the path is known, astronomers can estimate when the next crossing should occur. Tabby's star keeps taking that ability away. Each new dimming event changes the picture instead of confirming it. Predictions stop matching observations. The expected schedule never becomes reliable. The missing light remains real. The drops remain measurable. But the behavior no longer resembles an object repeatedly following the same path around a star. One option after another begins to disappear. Whatever is causing the dimming is not acting like a normal orbiting object. And the question of where the missing light is going becomes even harder to answer. For a while, the pressure begins to ease. The missing light is still there. The dimming remains irregular, but a different possibility starts to fit the behavior far better than a predictable object crossing in front of the star. Eye dust can drift, spread out, and thin over time. One region can block more light, another can block less. From Earth, the pattern would appear irregular, changing from one event to the next without following a stable schedule. That is exactly what makes dust so attractive as an explanation. Dust does not need a precise orbit. It does not need identical crossings. A large cloud can change shape, spread out, and move unevenly while still removing significant amounts of starlight from view. Suddenly, the strange behavior of Tabby's star begins to look far less extraordinary. The irregular timing no longer feels fatal. The changing depths no longer seem impossible. The missing light can be interpreted as the result of material drifting between the star and the telescope. Confidence starts to return. After losing one explanation after another, astronomers finally have a mechanism that appears capable of accounting for what they are seeing. The anomaly no longer looks untouchable. It begins to look solvable. And if dust is truly responsible, then the star should be leaving behind additional signs of that process. The dust explanation does not fail immediately. It fails when it is asked to make a prediction. If a large amount of dust is blocking starlight, that light does not simply disappear. The dust absorbs energy. It warms up. And warm dust should leave a visible signature of its own. Astronomers turn their instruments toward Tabby's star and look for that signature. The expectation is straightforward. If enough dust exists to account for the largest dimming events, then additional energy should be detectable beyond the visible light of the star. The measurements arrive. The expected excess does not. The star dims. The missing light remains real, but the amount of additional infrared energy falls short of what should be present. If vast quantities of dust are responsible for removing so much brightness, that changes everything. The problem is no longer whether dust sounds reasonable. The problem is that the prediction attached to the explanation is not matching the observation. The same idea that restored confidence now begins taking it away. Dust was valuable because it turned a strange event into a familiar physical process. It transformed an anomaly into something that seemed measurable and testable. But a test only helps if reality follows the prediction. Here, it does not. The dimming survives. The observations survive. Yet the strongest explanation begins to lose its foundation. The dimming remains in place while certainty collapses around it. And that raises a deeper problem. If the measurements are correct, what does that say about the way distant stars are being interpreted in the first place? The measurements never changed. Tabby's star dimmed. The light dropped. The observations remained consistent. What changed was the meaning attached to those observations. Again and again, astronomers compared the behavior against known explanations. A pattern seemed to fit. Confidence returned. Then a prediction failed, and that confidence had to be withdrawn. The star exposed a dependency that normally stays hidden. Astronomy often begins with light arriving at a telescope. From that light, researchers reconstruct what must be happening around a distant object that cannot be visited, touched, or directly inspected. The process works remarkably well, but it depends on a critical step. The interpretation must match every important observation, not just part of them. Tabby's star forced that requirement into view. The dimming events were real. The measurements were real. Yet, explanations that appeared convincing could still fail when tested against additional evidence. That does not mean the observations were wrong. It means accurate measurements and accurate interpretations are not the same thing. In the end, Tabby's star did more than resist a simple explanation. It revealed how conclusions are built from starlight, how those conclusions are tested, and how quickly confidence must be revised when predictions stop matching reality. The light was real. The measurements were real. The uncertainty lived in the interpretation. Tabby's star did not expose a failure of observation. It exposed how much depends on getting the interpretation right.